Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. You are invited to join us for the very first TWIMLcon conference, which will focus on the tools, technologies, and practices necessary to scale the delivery of machine learning and AI in the enterprise. The event will be held October 1st and 2nd in San Francisco, and early bird registration is open today at TWIMLcon.com. Again, that's TWIMLcon.com. I can't wait to see you there. All right, everyone, I am on the line with Bill Fehlman. Bill is the Director of Data Science at USAA. Bill, welcome to This Week in Machine Learning and AI.
Thank you, Sam. Thank you for inviting me.
Absolutely. So we were originally planning to connect at the Strata Data Conference in New York, but you unfortunately weren't able to make it due to Hurricane Florence, actually. Did everything work out okay for you with the hurricane?
It actually did. I mean, at the beginning of the week, we had a zone of uncertainty that included where I live, and then as the week progressed, it shifted south. So luckily, it missed my area, but still, it created a lot of uncertainty and drama in preparation for it.
I bet. So at the Strata conference, you were going to talk about topic modeling, and we're going to dig into that in our conversation today. But before we do that, why don't you tell us a little bit about your background?
Sure, absolutely. So as you mentioned, I'm the director of data science team at USAA, which is the United Services Automobile Association. And my team conducts research and applies advanced analytical methods in support of our contact center operations that serves 12.4 million members. And how I got to that position, my background is in mathematics, and I hold a bachelor's in mathematics, a master's in applied mathematics, and a PhD in applied science. And my applied science PhD dissertation, it was in the area of computer vision. And so what I did in my dissertation, I developed a method to classify non-heat generating objects in thermal imagery. And that work actually led me to an opportunity to work in an autonomy incubator at NASA Langley Research Center after I retired from the U.S. Army. And while in the autonomy incubator, I worked on a multidisciplinary team. I was doing computer vision, and what we were doing was developing machine intelligence software for uncrewed systems. And that computer vision work is what led me to my efforts at USAA involving natural language processing. And so what I'm doing at USAA is really looking in large corpus of documents and trying to identify topics, what I call unknown unknowns, really the things we don't know what we don't know. But if you go back to my computer vision, really computer vision is looking at frames of imagery, and each frame is a matrix where each value within the cells in the frame are either gray level values or RGB, red, green, blue. And when you look at natural language processing, I'm really dealing with large volumes of documents, and along with those documents, the terms or vocabulary that are involved. So I'm going to take those large corpus of documents along with their vocabulary, and I'm going to put them in a matrix. And so I'm really either when I'm doing computer vision or if I'm doing natural language processing, I'm applying the similar types of mathematics, which involves the calculus and matrix algebra, probability, and statistics to both types of applications. So it was a really good fit from what I was doing with computer vision and then transitioning over to natural language processing type work that I'm doing at USAA.
Oh, nice. And what's the motivation for doing that kind of work in support of a contact center? What are the kinds of documents and data that you're dealing with, and what business outcomes do they help drive for you?
Good question. So in our contact center, so we got a call channel We also have where agents are talking to our members on the phone. We also have a chat channel where members are talking to our agents as well. But also we have digital channels such as .com and mobile. So these are very large volume of both unstructured and structured data. And what we want to be able to do is gain insights in this data to better serve our members. And this is where actually topic modeling comes into play. And what you can think of topic modeling as a way to, what I like to say, uncover the unknown unknowns. There's the things we don't know what we don't know. And what topic modeling is an unsupervised method that helps us discover those topics that are emerging.
Got it. You mentioned a chat channel. Are you using AI as part of delivering that chat? And I'm mostly asking because this concept of discovering the unknown unknowns seems like it would be really helpful in identifying, for example, topics that come up in chat conversations that you might need to create, intents and support for in your chat system.
Yes, absolutely. So what we want to be able to do, and what we're doing is, you have chat in the chat channel. You have conversations between our agents and our members, and same thing with the call channel. And what we want to be able to do is identify topics that are emerging before we reach a peak call volume. And that way we can, say, mitigate members' concerns before we hit that peak call volume. As an example, if there's some kind of forest fire, for example, in California, or a hurricane, as we start seeing conversations about that, we can use topic modeling to get a better understanding of the needs of our members, and we can be able to be ready to provide the services before we even reach any kind of peak call volume. It's really being more proactive than reactive to the after the fact.
Okay. So you've got this data set that comes from is it coming primarily or solely from these chat and email interactions, or are you also transcribing voice support calls? How do you generate your data set?
So the chat, of course, that's through the chat channel, and that's text that's written between, the conversation between an agent and a member. And then the actual call is a transcription. So the call audio is transcribed to text. And so we would be able to obtain that data, which when we get it, it's redacted. So it's any kind of personal information or identifiable information or confidential information of our members is removed. And then we'll be able to run topic modeling on that to be able to gain those insights.
What approaches to topic modeling do you use?
So the approach or the methodology that I use mainly is what's called non-negative matrix factorization. So traditionally within the area of topic modeling, there has been mainly like three methods. The first method is one of the original methods, which is latent semantic indexing or latent semantics analysis. And what that method does, it takes a document term matrix. So you can imagine these very large. And by the way, when I say document, what I'm meaning is any kind of unit of text under analysis. It could be it could be one chat it could be a chat, or it could be a call transcript. It could even be a tweet or some other kind of unstructured data. But so you can imagine this document term matrix, and along the, say, rows are all these documents, along the columns are all these terms. So there's different methods that you can use to decompose that matrix into other matrices and be able to gain insights. And like I mentioned, one of the original methods is latent semantic indexing. And what that does, it uses singular value decomposition to decompose that document term matrix into three other matrices. And so, but the criteria with that method is that it's creating, or the matrices that are decomposed into are orthogonal vectors within each of those matrices. And so that is a concern because a conversation usually includes more than one topic. we could be talking, about Hurricane Florence, but we could also be talking about other topics involved as well. And we want to be able to distinguish those type of topics. And with latent semantic indexing, it usually has an issue doing that because of the orthogonality in the matrices that it decomposes it into. Another method is
before we continue. Does that suggest that this latent semantic indexing might be better used for smaller documents like a tweet or an individual chat message as opposed to an entire transcript of a call or an entire chat interaction?
It could be a tweet. But it's probably best applied when you don't have overlap within a given of different topics within a document, which would be it could be a tweet because you're restricted to the number of characters, so you're usually talking about one topic.
Is that kind of inherent to the document or to the set of classes that you are looking to associate these documents with? For example, or meaning, if I've got a news site and I have like some, strictly delineated, like a set of, like categories of news, like, health and finance and sports that are, orthogonal. Does that mean that I can use LSI, or is it have more to do with the content of the documents themselves?
It's probably more to do with the content of the document themselves, because you could be talking about, if you had like a large corpus of tweets, and let's suppose that they're talking about World Cup and the Olympics. If you take all of those tweets and you just put them into one bucket, then the latent semantic indexing might do okay with the tweets, since they may be talking about just different types of topics, and it may be able to distinguish them better than a call transcript that could include multiple different topics. And so that makes sense.
Just taking a step back, I'm thinking about the example that I gave where I'm trying to put documents into topics, and that's a different kind of a problem. That's more of a categorization type of a problem. Whereas what we're talking about here with topic modeling is like an unsupervised learning. Like you just have the data and you're trying to identify what the topics are in the data itself. Is that right?
Absolutely. And you can think of it as a form of soft clustering. Okay, so with the k-means clustering, for example, that's a form of hard clustering where it's actually taking a specific document and categorizing it within a specific cluster. But because we know that a document could include more than one type of conversation or topic or theme, we don't necessarily want to do a hard clustering to place that document within one specific cluster. What we would rather do is see how many topics are existing in that document, and then say, what is the probability that this document is associated with, say, topic number 1? What's the probability is associated with topic number 2, et cetera. So it's more of a soft clustering, is what topic modeling will do for you.
Okay. All right. So latent semantic indexing, it's kind of a traditional way that folks might approach this, but it's got this limitation because it enforces that these terms be orthogonal to one another, so it doesn't perform well when your documents have multiple topics in them.
Yes, absolutely. And so a couple other methods that work pretty well is one, a traditional method. It's called latent Dirichlet allocation, which is more of a probabilistic type method based on the Dirichlet distributions. And it does pretty good, but what we have found is that because it uses Gibbs sampling, which is more of a random selection of the terms in the documents, we see a tendency that the topics results vary from one run to another. And so that's where I sort of lean more towards the third method, which is non-negative matrix factorization. And what that does is it takes the original document term matrix and decomposes it into two other matrices, one being a document topic matrix and a topic term matrix.
Presumably because this isn't using Gibbs sampling, your results given a particular corpus are more repeatable?
Yes. So with the non-negative matrix factorization, what it's doing is it's more of an optimization process. So what it's doing is decomposing that original document term matrix into the two other matrices, and the goal is to minimize the error between the original matrix and the product of the other two. And it's pretty repeatable. I mean, it does a pretty good job at providing good results, and also that you can continuously run.
And now when I hear matrix factorization, I hear hard. Is that necessarily the case? I mean, or maybe hard to scale is maybe more particular. Do you find that to be the case, or are there methods for doing this matrix factorization that are, computationally tenable at large scale?
Yeah, so large scale, it does pretty good as, with using very large corpus sizes. I guess the challenge can be when you start running it on like near real time data, online data.
Okay.
And that can be a challenge, but there are different methods that can use the original topics and then do some kind of resampling of the new topics or new documents that are coming in and integrating them in.
So scalability to large corpuses isn't really actually a big deal, and the time it takes to do this can be a big deal, but there are some methods to overcome that.
Yes.
Okay, so interesting. So we've talked about this document term matrix as being the starting place for all three of these topic modeling methods. But we haven't talked about how we even get to that, how we represent the documents in this term matrix. There are different ways to do that, right?
Sure. So there's a pipeline for this process, and so what we do is we want to do some kind of pre-processing. So we may want to, of course, tokenize the documents. So each term is a single dimension. But we also want to remove things like the stop words. So the common terms like the high frequency terms that may not be able to give us very good insights with the topics or the subjects. So we remove those as well. And then we may want to also apply some dimensionality reduction techniques. So there's, of course, when you're working with a large corpus of documents, the dimensions can be very large, and that interferes with the processing time as well. So there's dimensionality reduction techniques that we can apply. What I have done in the past is, do a single phase or stage where I'm running topic modeling to help reduce the dimensions across all the documents as a pre-processing step as well.
And so what's an example of a dimensionality reduction technique that you might apply to this document term matrix?
So what I do usually as far as a dimensionality reduction technique is I will run non-negative matrix factorization on the entire corpus using two techniques. One is term frequency, forming a term frequency matrix, and the other method is using term frequency inverse document frequency. And so term frequency, what that's really doing is forming the original document term matrix that based on the frequency of terms, whereas term frequency inverse document frequency is looking at the frequency of terms within each document, but also looking at the frequency of a term across all the documents. So it's sort of like offsetting. So a very high frequency term that is existing across all the document may not receive as much weight as if it's high frequency, but only occurring across a few documents. And so what I'm going to do is I'm going to run the non-negative matrix factorization on the entire corpus at first and reduce my vocabulary size from, say, hundreds of thousands of terms to possibly down to a few hundred or 1,000 terms. And that is just the pre-processing. And then I can go ahead and get more refinement, running topic modeling further on those documents.
So how does doing your matrix, your non-negative matrix factorization on the larger document term matrix get you to reducing the number of terms?
So it goes back to the original decomposition. So the non-negative matrix factorization is decomposing the original document term matrix into the two other matrices, which are the document topic matrix and the topic term matrix. And so what it's going to do is you can reduce the number of terms based on the number of topics. So what it's going to do is, if you look at the topic term matrix, it's giving you the strength of association between the topics and the terms, so that if you have a term that has a higher rate, it has more of a higher strength of association with a given topic. So if I say look at the top 100 terms within a given topic and just consider those terms as part of my vocabulary that I'm going to use, then that will give me some kind of reduction, dimensionality reduction, as opposed to using all of the terms.
If you're looking at, say, these top 100 terms for a given topic, are you then kind of zeroing out terms back in your document term matrix and kind of creating more of a sparse matrix, or are you changing the shape of that matrix based on this new information that you have?
So it does change the shape. So what it's doing is I'm going to be my initial run with non-negative matrix factorization is going to create a new document term matrix, but only include those terms that will have the highest association that I had originally from the pre-processing run with topics. So what it's really doing is it's given me terms that are more relevant when I run subsequent topic modeling.
So just to kind of pull on this one, one more step. So you've got these terms, you zero out, say you've got 100,000 terms and you've got, well, how many topics would be typical in your case?
So that's a good question, actually. That's a sort of an open problem, the number of topics.
Mm-hmm.
But we have a technique that we run. It's to compute what is a coherence score, interpretability of the topics. And what that running the coherence will do is allow us to identify sort of like the optimal number of topics that we need to run.
And so is this on the order of tens or hundreds or thousands for, a corpus of documents that, well, maybe give us kind of general numbers for each of these things. How many documents do you tend to see, rough order of magnitude? How many terms, how many topics?
So it could be, we could easily be running, say, 50,000 documents through the topic modeling in one run. It could be more, but usually around 50,000. The number of terms, of course, it's going to vary. If we're running, creating a topic term matrix on a call conversations, then, the calls can vary from, a couple minutes to many minutes. So the size of the corpuses can vary as well, or the documents can vary as well. But it's all. The only limitation, of course, is the processing speed, that we're working with.
When you are identifying the terms that are most meaningful, is that on a topic by topic basis, or is that across the corpus? Specifically, I'm asking about this step where we're doing the dimensionality reduction, not so much like the meaning of the topic itself and the coherence. Specifically, when we're doing that dimensionality reduction and trying to get from our 100,000 terms down to 100, is that on a per topic basis, or are you looking at the 100 terms that have the most weight across all topics? Does that question make sense?
Yeah. So the final vocabulary is based on the terms across all the topics that were used in the pre-processing phase.
Okay. So you've got these, you identify these 100, say, terms that most strongly correlate to these topics that you've identified. And that kind of answers my question, I guess, that I've been trying to get to the long way around. If you're doing it across all of the topics, then you can just kind of get rid of all the other terms in your document term matrix, as opposed to if you were doing it on a topic by topic basis, then you'd still have kind of this potentially large sparse matrix.
Yes.
Okay.
And so this resulting set of vocabulary in this pre-processing that we just ran based on this topic modeling to identify the top terms across all topics across the entire corpus, this vocabulary set is what's going to be used in the subsequent topic modeling. And that's the dimensionality reduction.
You mentioned TF-IDF and term frequency. How do those play into here again?
So in the subsequent steps, I'm just going to be using TF-IDF. So in the pre-processing, when I do the initial run for non-negative matrix factorization, I use both techniques to identify the vocabulary, the term frequency and the term frequency inverse document frequency. But once I identify the vocabulary in the subsequent steps, I'll just be running the TF-IDF, which the difference between the two methods is that the term frequency it's really assigning an equal weight to each term. And so it's looking at how, for a given term, how frequent that term occurs across the entire corpus. But really, there's no difference on how it's applying the weight value to term A as it is to term B. But you may have a term that it's a high frequency not only in a given document, but a very high frequency across all the documents. So that specific term may not really give you much insights on the topic of the conversation. So the other method, which is term frequency inverse document frequency, sort of offsets that. It'll look at not only the frequency of the terms within a document, but also how frequent that term occurs across other documents. So it will give a high value when terms, for example, occurs many times within a small number of documents. And that's what I use in the subsequent topic modeling as well.
Then you mentioned the Coherence Score. What does that help you get to?
So you can think of coherence as a measure that captures the semantic interpretability of topics, and it's based on the co-occurrence of topics or topic words. And where that's important is that when the topic model, or say non-negative matrix factorization, is creating these categories consisting of these topic categories that are consisting of terms, we want the analyst to be able to look at those topics and say, oh, I get it. I understand what that topic is about. And that starts getting into interpretability. And you want to be able to generate a coherence score that is going to provide you a good semantic interpretability of the topics. And that's sort of like coherence score is a function of the number of topics. And so what we have done is identify the number of topics that will maximize the average coherence across the corpus.
And what's the intuition for kind of the math, the score itself, what the coherence score is saying?
So it's based on co-occurrence of words. So there's a few methods that are used, but what it's doing is it's looking at the counts of the number of documents containing like a set of terms, words, and it's using that, and it's also taking consideration the logarithm of that count. And so it's the closer for the specific coherence score method I'm using, the closer that value is to 0, the more coherent your topic is, and the more negative the value is, the less coherent it is. And so what we want to be able to do is identify the number of the topics that will maximize coherence, and then that's the number of topics that we'll use and be able to compute the topic categories and also the coherence scores for each topic category.
Okay, and that number of topics that maximizes coherence is going to be ultimately based on the relationships between these terms in the given documents in the corpus?
Yes, the co-occurrence, yes, the relationship between terms.
Okay. Do you have any kind of rules of thumb that you've found for, I guess it really depends a lot on the types of documents, but is there kind of a standard, say for call transcripts, do you have any rules of thumb where it ends up being on the order of, hundreds of topics as opposed to, tens or thousands?
So I've actually, this is probably surprising, but a rule of thumb is between 5 and 8 topics is a pretty good value to get good interpretability. If you start getting larger than that number of topics, then you start losing the coherence.
How does it fail? Like, are there patterns in the way it fails? Like, does it pick up words that, just aren't meaningful in the sense of, not particularly additive to understanding what the topic is of a given document? Or is it trying to, split topics to, fine grain? So there are words that are kind of similar that should be one topic. Like, is there do you see patterns in the way it tends to fail if you have too many topics?
I think what it will try, if you have too many topics, what it will try to do is spread those terms across more of those topic categories, and therefore you start losing the interpretability. But when you're doing topic modeling, it goes back to the purpose of it. It's doing soft clustering, so it's definitely possible that you're going to see a term existing in more than one topic category. For example, if I have 7 documents and 4 of the documents are talking about financial banks and 3 of the documents are talking about river banks, more likely you're going to see the word bank across those all 7 or all the topics, but you're probably going to still be able to distinguish the topics because you're going to see things that are talking about river banks in certain topics, and you're going to see things that are terms that are associated with financial banks and other topics. And the reason is because topic modeling is based on co-occurrence of terms. So you're going to see a lot of commonality of terms that are co-occurring together in those given documents placed in a specific topic. And it does pretty good. It does really good.
Is there a way to identify what the primary topic of a given document is? Is that just kind of ranking the topics based on some score or probability?
So that's a very good question, and that's actually one of the purposes of doing the topic modeling as well. So if you go back to the original decomposition, it's taken that document term matrix and decomposing it into a document topic matrix and also the topic term matrix. So the topic term matrix is giving you the strength of association between each of the terms and a given topic. So that if I say I take the top 10 terms for a given topic, which top 10 terms being the ones that have the highest weight of association with a given topic, that gives me information about what that topic or what is the theme of that given topic. But the other matrix, the document topic matrix, what that is doing is giving you the strength of association between each topic and a given document. And where that's important is it goes back to a conversation. So if you and I are having a conversation, we're probably going to be talking about more than one topic, but we may want to identify, well, what's the primary topic? And that's where that document topic matrix is important, because it will allow us to identify the topic that has the highest value or weight, which is the highest strength of association between that topic and that given document. And I can look across a given corpus and run topic modeling on a whole bunch of transcripts across a given corpus, and I can be able to identify not only the topics of conversations across all the documents, but also I can identify which documents had topic 1 as the primary topic of conversation.
You've done this factorization. You've got this document topic matrix and this topic term matrix. Can you then take this topic term matrix and kind of use it as a model that you can run inference against when you have a new document? You kind of put that through your term pipeline to get the terms in that document, and then you kind of multiply it by this topic term matrix to get the topics in that document.
So sort of like subsequent modeling, like subsequent.
Right. So trying to get the topics in a document that you didn't, or maybe the question, the question before this is, does this topic term matrix tend to have strong predictive value for documents that don't exist within the corpus that it was created on? It's not like a technique like supervised learning where you're built into the process, you're testing against data that you haven't built your model on.
Yeah, so I what you can do is, so the topic modeling is definitely an unsupervised machine learning method. But you can think of it as being a precursor to a supervised method. So you could really take the topic term matrix that is produced from this non-negative matrix factorization and look at each one of those topics that are as an output and label them. You can provide a label for each of the topic, and then create a supervised model, say with a deep learning model that is able to classify a new call into one of those topic categories. And then if you say go below a given threshold of probability, perhaps maybe it's a new topic, and you might want to put that new topic or that document associated with that one that fell below a threshold into a bucket and rerun topic modeling on it. So it's you can almost think of this process as a feedback. You're learning new topics and integrating them into a new model, updating the model, and then that model's making supervised models making predictions. And then if it isn't able to predict a new document based on a given probability, it puts it into a bucket and reruns topic modeling on it.
Given that you have this limitation of 5 to 8 topics in order to achieve interpretability or coherence, is there a process through which you might, if you've got a large corpus of, say, several 100,000 documents, or even this 50,000 document corpus, cluster your documents or partition your documents and create separate topic models, so as to maximize the number of coherent topics that you end up with?
Yeah, I think you could definitely do as one of the initial steps. You could create rules that would separate the documents based on the structured data, the metadata. And you might be able to, for example, calls. If the calls are going to the bank, within the bank, they might be going to deposits or checking or something like that. So as an initial step, you might be able to categorize those calls and then run separate topic modeling on each one of those categories. You might be able to do really just, it's a matter of looking at the structured data before you would separate them. And then once you got those bucket of categories, run topic modeling on them. So you would have different topic models.
So what you're suggesting is, as opposed to trying to do it in a machine learn kind of way, take advantage of the metadata, if you will, that's inherent in your problem to partition up your documents into, I guess there's a sweet spot, right? A small small of a corpus as possible, but that still allows you to create a robust topic model.
Absolutely. Really what you're working with is semi-structured data. You're working with the structured data and the metadata, and also, of course, the unstructured data, which is the text. And you're really combining the two to be able to do the topic modeling effort.
So you do this topic modeling, you get these topics, 5 to 8 topics from a corpus of 50,000 transcripts or chat transcripts. How do you then integrate these back into the call center operations to improve them?
So it goes back to the example I used. If we're identifying topics that are emerging before we reach a peak call volume, what we're able to do is be more proactive with the topics. We may be able to create better or inform our agents of these certain topics that are coming in, so they can be more prepared to mitigate any concerns or better serve our members. Mm-hmm. We may be able to even make adjustments if there's confusion about something that's say on the mobile channels, either .com or mobile. We may be able to make adjustments on those different channels because we're starting to see topics that are associated with those, and then that also in turn could decrease any call volumes associated with those concerns. But it's really trying to be more proactive to better serve our members rather than reacting after the fact.
And do you find that the initial steps of this process where you're doing dimensionality reduction end up being at odds a bit with trying to use this as kind of an early warning system because they get rid of emerging terms that might not have yet achieved some kind of critical mass?
No, not really. I think how we approach it's able to identify the most significant terms, and it's able to capture the most relevant topics. It does a pretty good job. It's able to surface the things that we didn't even know. I go back to the unknown unknowns, the things we don't know what we don't know. It's able to surface those things, so we're able to take action on them.
Awesome. Are there any open challenges or problems that you see recurring as you try to use these types of models?
I would say there's definitely open problems. I think that choosing the number of topics is still an open problem. I mean, I mentioned that we use the Coherence Score to try to maximize coherence. What is the number of topics that will maximize coherence? I still think that's an open problem. An appropriate corpus size, I think that's still an open problem, as well as the document term matrix. There's different weights that are used in a document term matrix, such as the term frequency and term frequency inverse document frequency. But I think there's more room for developing new weights and doing more research in that area. And then, of course, I talked about coherence. The coherence is the interpretability of topics, but I think also determining the relevancy of topics is really important, because something could be interpretable, but is it really relevant, and do we need to take action on it?
Well, Bill, thanks so much for taking the time to chat with us about this. I'm sorry that you didn't get a chance to present this at Strata. I'm sure folks would have enjoyed it, but it's really interesting stuff.
Well, thank you, Sam. And once again, thank you for inviting me.
Absolutely.
All right, everyone, that's our show for today. For more information about today's show, visit TWIMLai.com. Be sure to visit TWIMLcon.com for information or to register for TWIMLcon AI platforms. Thanks again to C3 for their sponsorship of today's episode. To check out what they're up to, visit c3.ai. As always, thanks so much for listening, and catch you next time.